For our final section of Unit 4, we're going to go ahead and start Chapter 6. This will be the only section we do from this chapter, and after this we'll take a test. I mean, we'll do some others, but for this unit, it's the only one we'll cover. Section 6.1 deals with inverse trig functions. Your book calls them circular functions, but remember that that's just referring to the unit circle. So it's inverse trig functions. This is something you don't necessarily need to know for this section, but it's good to kind of talk about it and remind ourselves of it from college algebra. Remember that the horizontal line test tells us that a function is 1 to 1. That means that every x has exactly one y value and every y has exactly one x value. And we can tell by looking at the graph if it passes both the vertical and horizontal line test. Make sense? So for example, a parabola is a function because it passes the vertical line test, but it doesn't pass the horizontal. The horizontal line test, it fails, and that tells us that the inverse is not a function. In order for a function and its inverse to be a function, it has to pass both the vertical and horizontal line test. And so when that happens, we call that 1 to 1. Now here's the problem. Because all trig functions are periodic, their graphs all fail the horizontal line test because it happens over and over again. So they'll pass the vertical line test, but they will fail the horizontal line test. That means that none of them is 1 to 1. In order for a function to have an inverse function, it has to be 1 to 1. You have to have one y value for every x, one x value for every y. In other words, the answers have to be unique for an inverse function. Okay? For that reason, a long time ago in trig, they decided which piece of that function we would use when we deal with inverse functions. We'll only do a small piece, okay? Now we're not actually going to graph here, but it's based upon the graph. They chose a small piece. So a long time ago, just arbitrarily, they decided which values would be the answers to the inverse trig functions when the question was posed in such a way, okay? So it's been restricted. This ensures that the output answer will be unique. Before we kind of really get started and I kind of explain to you what's going on here, I want to caution you that the -1 in f to the -1 is not an exponent. What does it stand for? Inverse. Yeah, if it's attached to a y or an f of x or a g of x, it stands for the inverse function. Also note that instead of standard inverse notation above, trig function inverses are often notated with the prefix arc instead. They just mean the same thing. So for example, I might have a problem that says f inverse of x. I might have one that says sine inverse of x. I might have one that says arc sine of x. And this is just left over from a time when it's just easier than typing superscripts. So they came up with this, and this also means the same as inverse. So arc means inverse. So it could be written either way, and your book goes back and forth from the -1 power, which really just means inverse, to arc sine. Make sense? Okay, now I'm going to give you a slide, and it's going to have a bunch of information in it. I want you just to let me talk about it first, and then we will actually decide which portion you need to memorize and which you don't. Because it is important that you know some of this, but at times there's just an overabundance of information there. So just let me kind of talk about it with you, and then we'll sort out what you actually need to know. Okay? It's kind of busy. All right. So here's what we have for inverse trig functions. First off, notice that the inverse trig functions are restricted to 2 quadrants each, so that the y values, or the range, are unique, meaning there is one quadrant for the positive and one for the negatives. When we do inverses, do you remember how an inverse reverses the domain and the range? So with a regular like y equals sine of x, we put the angle in and we get a value out, right? And the angle could be pretty much anything that we put in, but it will spit out an answer between -1 and 1. So these used to be the ranges right here. But when you use inverse trig functions, inverse sine, inverse cosine, inverse tangent, inverse cotangent, inverse secant, and inverse cosecant, the range of the original becomes the domain. Okay, so you actually already know these. So you're not going to spend a whole lot of time worrying about these because you kind of already memorized those a long time ago as the ranges of the trig function. So the range of the original is now the domain of the inverse. what you need to really kind of understand is this. And I actually think that I can show it to you a better way than what your book has done here. It's important to understand before you really can do anything that the answers to inverse trig functions are the angles. So rather than me saying, what is the sine of 30 degrees? What is it? What is the sine of 30 degrees? 1/2. Instead, I would say, give me the inverse sine of 30 degrees. Let me try that again. The inverse sine of 1/2. And your answer to that question is going to be 30 degrees. Make sense? Okay, so for this section, when we're dealing with inverse trig functions, your answers are usually angles. Okay?
Could it also be?
Now, here's the problem. Here's the problem with those. How many times does sine equal 1/2? We know it happens at 30 degrees, but it also happens at 150 degrees, right? And it also happens if you add or subtract 360 from either one of those. So see, there are infinitely many answers to that question. Does that make sense? But we need to have a standard answer. Do you tell me 30? Do you tell me 150? What do you tell me when I ask you for the inverse sine of 1/2? And the answer is you give me the quadrant 1 answer. You always give me the quadrant 1 answer between 0 and 90 or 0 and pi over 2 if it's positive. That's what they're saying here. So for anything that's a positive value, notice you're going to answer from quadrant 1. Make sense? So all that leaves us to worry about is how do we answer if I say, what is the inverse sine of negative 1/2? What quadrant do you choose that from? Well, that could come from quadrant 3. It could come from quadrant 4. Or it could come from subtracting, 360 from one of those. So the question is, where does it come from? And here's where things go bad. For inverse sine and inverse tangent and inverse cosecant, you give your answers, if it's a negative input, you give the output from quadrant 4. So they come from quadrants 1 and 4. And that is sine, its reciprocal cosecant, and tangent will come from quadrant 4. But you're not allowed in inverses to go over pi or 180. So because you're not allowed to go bigger than 180, you have to give it as a negative answer. So see how these guys right here have negative possibilities for answers? And so that's why it gets really hard to start sorting out. For the other 3, cosine, cotangent, and secant, you give your answers if they're positive from quadrant 1, but from quadrant 2 if they're negative, even though there are other places where they're negative. You just give them from quadrant 2. And that's just part of what you have to memorize. What quadrant do I give the answers from for which of these? And on the next page, I'm going to actually sort it through with you so that you don't really have to write anything down from here. The nice thing about those is you just go from 0 to pi or 0 to 180. See these? Do you know why these guys are broken right here? You see it, how these are broken? Those are asymptotes. So you don't have to memorize that. You'll know it if you ever see it, if you get it undefined there. But there's an asymptote there because it happens to be undefined there. Okay, so we're going to pause for a second, let you kind of ask any questions that you have, and then on the next slide, you can actually take notes. Okay, so let's see what notes we kind of want to take here. This is going to tell us how to answer an inverse trig function problem. First off, use radians unless you're told otherwise. So your answers are going to be in radians. Typically with this book, if they give you y's and x's, those are radians. But if they use thetas, they usually want degrees. original problem has a positive function value, you just give your answer from quadrant 1, no questions asked, regardless of what trig function it is. So if it's positive, you don't worry about it, just give it from quadrant 1. So the questions only pop up, what do I do if they are negative? And that's where it's broken into 2 different pieces. Okay. If the problem is negative, so if you have a negative function value, here's what we do. For inverse sine, inverse cosecant, and inverse tangent, you give that answer from quadrant 4, but you answer with a negative angle. So from quadrant 4, but as a negative angle. So you wouldn't say like, let me think of one. I don't know, where's the 45-degree reference angle that's over in quadrant 4? Do y'all remember how to do those? It's 1 less than twice the bottom, right? In radians. So that would normally be 315 or 7 pi over 8. 4. I can't talk. 7 pi over 4, you're right, 7 pi over 4. So you wouldn't answer it with those. You would answer it as negative 45 degrees or negative pi over 4. You never go larger than 180 or pi. So it must be smaller than pi or 180 degrees. You're never, pi is the biggest you can go, 180 is the biggest you can go. If you need something from quadrant 4, you back yourself off into the negatives. Okay? Now the other one's easier. If you're dealing with inverse cosine, inverse secant, or inverse cotangent, just give your answer from quadrant 2 as you normally would from the unit circle. And that's only for negatives. Everything else is going to come from quadrant 1. So we'll pause right there, make sure everybody has those notes taken, and see if you have any other questions yet. So one last thing to note here. Quadrant 3 is never used at all for inverse trig functions. Now for other things it is, but if it's an inverse function problem, you never use quadrant 3. So let's do some examples.